Now, propagation. Okay, we learnt that they are electromagnetic waves and they travel from the transmitting antenna to the receiving antenna. That's what we call propagation. They always travel in straight lines. Now, if that was the case, radio would be really boring. They can be refracted, reflected and diffracted on a variety of things. So the further that waves get away from transmitting antenna, they become weaker. It's actually, you don't need to know this, but it's the inverse square law. So double the distance, quarter the power. So by the time signals get to you, there's not much getting to you, if you think about it. So anytime it travels through free space, becomes slower, becomes weaker. Now, above us, there is the ionosphere, which is the key transmission medium, if you like, for for all RF, but the key one for us is for the HF, high frequency spectrum. We break up, and through research they have worked out that there are 3 layers during the day, and so these layers are created by the sun ionising particles within the atmosphere, and each of these layers have different characteristics. So during the day we have a D, E, F1 and F2 layer. During the night the D and E layer combine. So slightly different, and in fact that's during the night you can suddenly hear AM broadcast stations from interstate at night. And if you think about it, if you think about the geometry, the D layer is lower, and so during the day the geometry is less distance, doesn't quite go as far, whereas when D and E layer combine, you think about it, the geometry actually makes the signals go further. That's why you end up hearing Melbourne AM radio stations at night. Each of these layers respond differently to different frequencies. This is a good diagram. It shows the very first one at 7 megs. So this is 40 meters. That signal goes up, gets refracted off of the E layer and back down to ground. So that's a good example of the geometry. It goes a certain distance. If we go to 20 meters or 14 megahertz, it goes up to the F2 layer, which is an even higher layer, and goes even further. And 20 meters is what we call a round the world band. You can work the world on 20 meters. Whereas 2 meters, 144 megahertz, not affected by any of the layers, goes straight through, keeps going. Great for a satellite, because the satellites are above that. So yeah, the bending is dependent on the layer, its density and the frequency of operation. We introduced the concept of there being a sunspot cycle. So sunspots are exactly that. They're dark spots on the sun. They're centres of activity in the sun that potentially throw some energy towards us, which is good for us because that's where we get novel propagation methods. The sunspots tend to peak on about an 11-year cycle, and if you look at the very end, we're about to go into a peak, and in fact our sunspot cycle's really good at the moment. We're getting some fantastic, we're already getting, we're still getting VHF and UHF openings into Japan and a few other things, which is unheard of. They would have disappeared by now. And so the sunspot cycle's peaking, which is really good. As you can see, back in the 1950s, 40s and 50s, the sunspot cycle was off the show. And in fact, a lot of older amateurs would say, oh, you could work the world on a wet piece of string. Didn't need much at all. So So yeah, we're not quite getting to that, but it is improving quite dramatically. The amount of refraction is dependent on not only the sunspot cycle but the time of day, because at night the DE layer disappear. So there's different characteristics, and also the season. And I talked about at VHF and UHF and microwave frequencies, we are still able to communicate much longer distances, whereas we would normally only be able to do that in the middle of summer. So, mind you, the northern hemisphere is going into summer, so they're going off, and we're at on the other side of that cycle. Bit of extra information. You'll notice that there are some different terminology that we use. There is what's called that antenna is greatly exaggerated, but we need to take into account the curve of the Earth, obviously. Those waves that travel along the ground are what we call, funnily enough, a ground wave. It can only go a certain distance. Whereas if we refract something off the ionosphere, an upper layer in the ionosphere, we call them sky waves. And you can get this funny situation, it talks about selective fading here, where the ground wave and a sky wave get to the same point, and they can, dependent on the phase of the sky wave getting to the ground wave, you can have enhancement, so you can have a really good signal, or quite the opposite. You can get selective fading. It's actually the signal disappears. So you can get some interesting scenarios. Now, VHF and UHF, I showed that diagram where 144 goes straight through all of the layers and keeps going. VHF, UHF and frequencies above, so microwave frequencies, are what we call line of sight modes. You need to be able to see what you're trying to work, or have something to bounce it off, like Mount Wellington I talked about earlier. It is dependent on the height, the transmitter power and the receiver sensitivity. If you've got things in between, large structures, hills, trees, buildings, whatever, generally doesn't get through. However, it can be bent over and around particular objects. So these are interesting arrangements. And it also can be transmitted much longer distances through what we call tropospheric ducting. So this is where you get a warm body of air enclosed by two cold bodies of air, and it creates an inversion layer. Now, inversion layers, we don't tend to get them too often down here, but if you're up in the northwest and you're looking across Bass Strait, you can see inversion layers. There's a particular layer that you can see, which is a warm front and a cold front coming together and creating this layer. And that particular tropospheric duct has the ability to a signal to enter the duct, bounce around in the duct, and then drop out somewhere else. And so we have things like Hepburn charts. Mr. Hepburn takes a whole lot of the weather data, and he comes up with these charts, which enables you, global charts, which enables you to tell where potentially these ducts exist in the world. And that's how you get VHF and UHF frequencies that go a whole lot more than line of sight distances. We talk about knife edge diffraction. So this is bending or diffracting a wave around a hill. If you've got a really sharp object, that receiver shouldn't theoretically be able to receive any signal because the hill's in the way. But it does get signals because they are diffracted through the knife edge of the hill. The tropospheric duct. This is cold air. This is warm air enclosed by two cold air layers. Goes in and drops out somewhere else. And tropospheric ducting is more common than you think. So yeah. Now, a radio wave is radiated from an antenna and the wave travels further because as it travels further it becomes weaker, well and truly, much weaker in fact. Long distance HF propagation is a result of... Correct. And this is, you probably need to do a deduction here. Ground waves, okay, that's HF propagation, but ground waves don't go anywhere near as far as sky waves. So probably not ground waves. Knife edge diffraction is a VHF and above mode. Tropospheric ducting is a VHF and above mode, so it's got to be ionospheric refraction. It's just a deduction. VHF, UHF signals can be obstructed by large objects. Easy as that. Anything really, actually. Trees, buildings, whatever. VHF, UHF signals, long distance communication is possible mainly due to
atmospheric conditions.
Yep. The magnetosphere is above, way above the ionosphere, so we're not even talking about the magnetosphere. It's just, that's a furphy. Atmospheric conditions, could be. F1, F2, that's HF. And VHF and UHF skipping off the upper atmosphere. It doesn't, it goes straight through.